All right. So, a couple housekeeping stuff before we get going. So we'll kind of pick up where we left off, talking about multiple linear regression. That kind of third problem set. I got up the first half of it. I kind of want to see how today goes before I post the second half. So you should be able to work, I think, through all except for maybe one of those questions that I posted. I'll post the complete version tomorrow morning after I might even get up this afternoon, but kind of based off of what we get through. Yeah, the problem set for number 3, I posted it last week after class. So I only put up the first part of it, right? So you should have everything that we worked through last week was enough to kind of get through everything except for maybe one of the questions, right? Might be a little more clear after today. So I'll post the kind of complete problem set tomorrow based off of what we covered today. Okay. So you should see kind of this get updated. I'll probably just get rid of part 1 and just post the complete version of that problem set. But I wanted to get it out there so you could start working on the stuff that was kind of covered last week. Okay. So I currently have, it's not what I want. Go back. So you've got here. So I just kind of have that Word doc and the data. So I'll create the new assignment that kind of has the actual due date on it. So that due date will be, we cover it today. So that should be the end of next week on Friday. Okay. So after we cover it today, you'll have a good amount of time to still kind of work through that problem set. I just want to get it out there early if people wanted to work on it early. Now it's also going to get posted after class today. We should have worked through enough stuff. I have the practice problems up there already, but that third quiz you'll see pop up. Okay, so that'll get posted tomorrow. So today, so that'll get posted tomorrow with that third complete problem set. So that quiz is going to be due by the end of the day on Monday. Right. So the majority of that and the practice problems we already kind of went through last week. There's a little bit that we didn't cover, so I wanted to make sure we covered that today and kind of give you a little bit more time to kind of practice for that. So that'll be due next Monday at the end of the day. Okay, so you'll have plenty of time to kind of review those materials. You could have already started reviewing them. So you'll have that quiz and that problem set that are both due next week. The quiz due on the end of the day Monday, problem set due at the end of the day on Friday. Okay? So I can't stress enough, if you're having issues with that problem set, office hours are a great time. I'll let you know in advance. Like tomorrow, we're going to be very busy because my B251 students are not happy with their exam scores. So I'm sure it'll be pretty busy, right? Next week is probably going to be a little bit less busy. So Monday and Wednesday of next week, if you're wanting some kind of help with the problem set, might be a little bit easier to kind of, you won't be waiting as long if you stop by. Okay. So that's kind of the housekeeping stuff where we're going. I've also had up for a while that practice exam. That's going to be, I think it's March 5th. I'm doing this from memory correct. It's in the syllabus. So we've basically got what, this week, next week, and then that Thursday of the following week would be. So that week that we have the exam, that Tuesday's class should just primarily be review. I'm guessing where we're currently at, next Thursday's class will also be primarily review. All right. So we'll have new material this week, new material next Tuesday. It might bleed over a little bit in that Thursday where we have one more topic to cover, but primarily we're going to have 2 class periods of just being able to do review. Now, when it comes to exams, I'll kind of, give a little bit more kind of instruction of what that's going to look like, kind of the layout, get somewhat of an idea from this practice exam. It's going to be a lot of short answer, right? Maybe a couple multiple choice questions sprinkled in there, but primarily kind of short answer questions. You're not going to have to give me any specific lines of code, but I might give you lines of code in the output and you need to know how to use that. All right. So in the sense of I've had questions that stayed a part of the exam, well, yes, right. Any of these in-class questions, any of these quizzes, a lot of times I'm giving you state output, but I'm not going to be requiring you to tell me the specific code that kind of produces that, right? Is that making sense? Any questions for me before we kind of dive into material?
When you say state out, that usually mean like one of those like tables you give us, like.
Yeah, so up to this point, we've primarily looked at, we've looked at covariance matrices that we have to use. We've looked at regression output. So it's going to be anything that Stata would produce for us in terms of, these tables and these, how we identify the statistics from them. Is that? Yep. And like I said, we'll have plenty of time to kind of dive deeper into that. Should have 2 like almost full class periods where we can do review, take a look at this practice exam. And this practice exam is meant to be very similar to what you'll see on that exam. Right. So if you take a look at this, you'll kind of get an idea of what the layout looks like. Okay. Any other questions from me before we dive into the material?
One of those, I apologize, sorry, one of those files was the sheet, will we have that?
Yeah, so you'll have that formula sheet for the exam as well. Yep. I didn't say that yet, but that's why I put it up there. You'll have that with the exam. So as you're kind of going through the practice exam, you would have that formula sheet in front of you for the exam itself as well. Any other questions? Okay. So where do we leave off? We started talking about multiple linear regression, right? We're trying to predict a variable. Having one variable to predict it was not very good, right? So our R squared was going to be relatively what? R squared tells us the amount of variation we can explain in that Y variable. So if we only have one variable on the right-hand side there that's explaining Y, our R squared is going to be relatively, using one variable to predict something, am I going to be able to make very good predictions? No, I'm not going to be able to explain a lot of the variation. R squared is going to be probably relatively low. Right? Now, as I add in more variables, if I'm trying to predict somebody's GPA with what their course load currently looks like, right? What their previous courses were, what their IQ level is. As I add in more variables, what's going to happen to my R squared? Am I going to be able to make better or worse predictions if I'm adding in additional information? Better, if the R squared, the technical interpretation is the amount of variation and why we can explain. But if you just want to think about the R squared as essentially a higher R squared is telling you you're making better predictions or you're making more accurate predictions. Okay? So as we add in more variables, our R squared should go up. Right? Now, there's a little bit of a caveat to this, right? So we have our R squared, and that's just the proportion of the amount our model explains versus the amount of total variation in Y. We don't have to get too lost into kind of this technical interpretation, but right, it's going to be the amount of variation our predictions explain over the amount of variation in the actual Y values. Okay. So we were looking at this, we said, okay, if I use one variable, the R squared is going to be relatively low. All right. Being a student athlete, how much of the variation in GPA does that explain? What? This isn't probability, so it's what, 0.8%? It's pretty low. Right? Now, if I add in an additional variable, what should happen to my R squared? It should go up. So if I add in this SAT score variable, notice what has happened to my R squared. I'm now able to explain 16% of the variation. So I could also think about it when I add in this additional variable. This isn't quite technically correct because we talked about omitted variable bias last class. But how much more variation is this SAT score allowing for me to describe or allowing for me to capture? Well, if I went from 0.8% to 16.7, what, roughly 16 additional percent or just under 16, right? So I have a much more accurate, a model that's much more accurately predicting my Y variable college GPA, okay? So we've got a higher R squared. So this is where we want to then add in this additional statistic. And I think I introduced this before, but we're going to go, okay, this is just going to be my way today. So we're going to talk a little bit more about, we already looked at how the sample size would affect our adjusted R squared, but we're now going to talk about how adding in more variables is going to impact it. So my R squared, we had was the kind of proportion of variation my model explains over the total amount. And this SS was sum of squares, but we can think about if you want to interpret sum of squares just as variation, might make it a little bit easier. So that's going to be the same. So this fraction represents the proportion of the variation, I guess, and why we can explain. So what's another way of saying that? I could take 1 minus the proportion what? This is the proportion I can explain. That should be the same as 1 minus the proportion that I can't explain. Okay? So there we would kind of call the residuals or our errors. That was what we couldn't explain, right? That was the error in our model's predictions. So here, the proportion of variation I can't explain, if I subtract that from 1, R squared of 1 means what? I'm explaining all of the variation, right? So this is just another way of kind of writing our R squared. So what we're going to do when we talk about the adjusted R squared, and I think I mentioned this before when we talked about the role of sample size, a lot of the times you'll see like R squared adjusted with a bar over it. I'm not trying to trick you. I'll usually just use a subscript to kind of, really make sure we know we're talking about the adjusted R squared. So what we're going to do with the adjusted R squared is we're going to use, this form of our R squared equation. So 1 minus the proportion we can't explain. But we're going to scale it by this additional factor. So this a factor that we're going to scale the proportion that we can't explain by is n minus 1 over n minus k minus 1. Okay. So we talked about the role of n. So first of all, what is this fraction always going to be greater than? If I take n minus 1 and then n minus some value minus 1, what is true about the denominator? It's always going to be smaller, so my fraction is going to be above 1. Okay. Now, if I increase the sample size, this is a thought experiment we went through before, and you could go through a very extreme version. Let's say I was only including, k represents the number of variables in my regression. So when we started out with a simple linear regression, if I had one variable and a sample size of 4, this fraction would be what? 3 over 2, okay? Or the scaling factor would be 1.5. What happens as I increase n? Well, just to give it a thought experiment, what if n was 100? I would then have what? 98? Nope, sorry. 100 minus 1 is 99 over 98. What is this fraction getting closer to? I mean, this is approximately 1, so it's going down. Right? As n goes up, this scaling factor will go down. If this is getting lower, what's happening to the amount that I'm subtracting? So if I'm subtracting this amount, and this scaling factor is going down, the amount that I'm subtracting, right, is going down. But if I'm subtracting a smaller amount, what's happening to my adjusted R squared? Subtracting a smaller amount is going to increase it. So this is the idea that even if I had the same models, but I can't explain the same amount of variation, having a higher sample size, right, should mean that the amount of variation I can't explain, that's more powerful because I have more data that is allowing me to explain that proportion of variation. Okay, so increasing n is going to essentially help our adjusted R squared, right? It's going to cause it to be higher. Now, if instead I want to go through the second thought experiment, and I'll try to use colors here. Eye doctor 1 or 2, probably 2, right? It's better at showing the color a little bit. Okay. So here, let's use that same adjusted R squared equation. So it's the proportion that I can't explain, subtracted from 1, but we're scaling it by this factor of n minus 1 over n minus k minus 1. Okay. So as I increase the number of variables, we're now looking at multiple linear regression. So if I start including more variables on the right-hand side, what's always going to happen to R squared? We said it's always going to go up. But if I have to use more variables to do that, our adjusted R squared kind of penalizes me for that. Because I can just throw shit at the wall and hope it sticks, right? And so if I'm just increasing the number of variables on the right-hand side, I can always get my R squared to go up. So the adjusted R squared kind of penalizes me for just throwing random stuff and hoping that it increases R squared, right? Because I know that it will, even if it's a small amount. So if I increase the number of variables k that I'm using on that right-hand side to make my predictions, if I subtract a larger amount here, what's happening to my denominator? Well, if I had more variables in my sample size, but just in terms of directional, let's say n is like 1,000, and I am including, instead of 5, I'm going to 10 variables. So I've increased the number of variables. What's going to happen to this fraction? I'm subtracting a larger amount, so it's going to go down. If I'm dividing by a smaller amount, what happens to my scaling factor? It goes up. If I'm subtracting a larger amount, and sorry, this larger amount was kind of this entire thing, what's going to happen to my adjusted R squared? Well, if I'm subtracting a larger amount, my adjusted R squared is actually going to be going lower, right? I mean, this is just, we're kind of thinking through the directional changes of this equation. So increasing the number of variables I'm including. If you just want to think through the intuition, this scaling factor is penalizing me for adding in more variables. So if it's penalizing me, what's going to happen to my adjusted R squared? It's going to be lower than before. Okay? Even if I can explain the same amount of variation, I have to do so using more variables. It's penalizing me for that. Okay? So we have kind of the summary of this, and you can always kind of walk through these directional changes. But in the first case, we said, if we increase our sample size, that's always going to make our predictions more accurate. So our adjusted R squared isn't going to be penalized as much. Now, if instead we get that same R squared from a higher number of variables, but we had to use more variables, so that scaling factor penalizes us. So there, what's happening to my adjusted R squared? It's going down. So this is where when we get closer to the exam or you're thinking about this third quiz, you can, I guess, memorize this, right? This is going to be the end result. But if you just have the equation in front of you, whoever asked about the formula sheet earlier, right? You can kind of think through what's going to happen if I increase or decrease n, right? That would have the exact opposite effect. Or if I increase or decrease the number of variables I've included on the right-hand side. But the intuition is always there. If I increase my sample size, my predictions should be more accurate. My adjusted R squared will be higher. If I have to increase the number of variables I'm including, well, there, I'm just throwing stuff out there to try to get better predictions. My adjusted R squared is going to get penalized for that, or it's going to be lower. Any questions on that idea? Yeah.
When using multiple, sorry,
You're
when using multiple independent variables, is it always better to use adjusted R squared, or is there a certain point where it penalizes it too much, or penalizes it not enough?
So in general, we want to, if we're comparing models, like not we're looking at different models, we've included more variables, or we're looking at different sample sizes, we always want to use the adjusted R squared, right? And that's kind of comes from the fact that we already know that if I increase K, I'm always going to get a higher R squared.
Yeah.
And so what we really want to do is, it's almost like the adjusted R squared is almost like the average amount of variation each variable explains, right? So as I add in more variables, even if I could explain the same amount, each variable is explaining a smaller amount, like per variable. Right. It's another way of thinking about the adjusted R squared.
Yeah.
And so when we're comparing models that have different number of right-hand side variables or different numbers of predictors, we want to be able to compare, even though I have one regression where I've got 10, one regression where I've got 20, I want to be able to compare those. I know if I've included 20, the R squared is always going to go up. And so that adjusted R squared allows me to kind of compare across models. Is that?
Yeah.
Any other questions on this idea? Okay. So kind of talk through the adjusted R squared, kind of talk through some of the directional changes. So here we can kind of look at this. Excuse me. When I only have one variable here and a pretty large sample size, well, that as that scaling factor gets closer and closer to 1, what's going to happen to the difference between my adjusted R squared and my R squared? So if we look at those two equations, here was my R squared. Here was my adjusted R squared. If this is getting closer and closer to 1, let's assume it was 1. What do I have? The exact same value. So as my sample size goes up and the scaling factor goes down, getting closer and closer to 1, what's going to happen to the difference between my adjusted R squared and my R squared? Well, they're converging towards each other, right? So you'll notice when I have a really high number of observations and just using one variable, what's the difference between the R squared and adjusted R squared? 0.0002. It's very, very small. Now, if I had a different regression where I'm increasing K, it still should be the adjusted R squared and R squared are pretty close. But because I've included more variables, that adjusted R squared is penalized for that. The R squared isn't. So what's going to happen to the difference between my R squared and adjusted R squared? It's actually going to be getting larger as I include more variables. So you'll notice here, it's still pretty close, but at least now the difference is to the third variable instead of the fourth, right? It's getting further away, okay? Now you'll notice with high sample sizes, I said if you increase n, R squared and adjusted R squared are gonna be closer and closer together. So when we have like 4,000 observations, there's not much of a difference there, right? But we're dealing with smaller data sets, that difference is gonna be more pronounced, okay? So I had this slide left open. I kind of went a little bit out of order. We already kind of covered this, right? Kind of the directional changes of n and k, how they impact our adjusted R squared. I don't want to take time today to go through this. If we have extra time based off what we covered today, I might do this on Thursday, but we can walk through some simulations to prove these things about the R squared and adjusted R squared to ourselves. I'm hoping that we could have time for that on Thursday. So we'll probably revisit this concept just to get a refresher on it, okay? But what I wanted to focus more on today is this idea that when we use multiple linear regression, we can use continuous variables, but we can also use these other variables we're looking at, which we call dummy variables or indicator variables, right? So what did a dummy variable do? I haven't really set this up. We were just looking at simple linear regression. All it was doing was changing kind of our intercept. So maybe a different visualization of what's happening when we have multiple linear regression. So I think the example I had here, I was using, we were trying to predict wages, right? And I think these were hourly wages. It doesn't really, right? We're just scaling them however they are. So we're trying to predict wages, and we're going to be using IQ. So if we did run this regression, what do you think the sign, if I think about, I've got my intercept, I've got my IQ variable. I want to make sure I do this the same order as the slides, just so. And I've got this dummy variable or this indicator variable that says it's a 1 if the individual is in the data classified as being black, 0 if not, okay? So if I was looking at the data, maybe it looks something like this, right? So like, here's my scatter plot. Obviously, probably the data is more varied, but just to kind of make the point, it's kind of a nice tight distribution. So when I go to estimate this line of best fit, if I'm looking at the relationship between IQ and wage, what is the slope of that line of best fit? It's simply beta 1, or technically the estimate I get from my data of what beta 1 is. Now, for an individual who is considered non-black, what would this variable be? 0. So what is the intercept for that line of best fit for individuals who are kind of coded in this data as being non-black? Well, the intercept would simply be beta 0. Okay. Now, if instead I had, and I'm coding it in colors to make it a little bit easier to think about, when we look at the actual data, unfortunately, it's not in colors, right? We only see the data points. But let's say I had something that looks like this. And every individual here, I've been able to identify using this color. These are all the individuals in my data set who were classified as being black or had a 1 for that indicator variable. Now notice, if I want to know the relationship between IQ and wage, or I want to know the slope of this line of best fit, what is it still? It's simply beta 1, right? Because beta 2 tells me kind of the effect of if I'm coded as being black versus non-black. The actual relationship between IQ and wage is still simply captured by beta 1. So what has this dummy variable done in my multiple linear regression? Well, if I think about the intercept now, for an individual who is black, how do we interpret the intercept? It's the value, the predicted value of wage, if all other variables are equal to 0. So when the variables here were equal to 0, when IQ was 0, the black variable was 0, here was our line of best fit. That was simply the intercept. When I include a dummy variable, what it's saying is, what is my predicted wage now for an individual who's black? Well, we're starting out, the intercept is when IQ is equal to 0, so that doesn't really matter. But if the individual is coded in our data set as being black, this variable becomes a 1. What is our predicted wage now? Beta 0 plus beta 2. So by including these dummy variables, it allows us, we're still picking up the same relationship between that continuous variable IQ and wage, but it's changing the starting point of that predicted wage. So in the example that I have here, what must be true about the sign of my prediction for beta 2? If it's starting out lower, that must mean that beta 2 is negative, which this might be a regression we could run. It's the same IQ values. What is my predicted wage? What would beta 2 actually be maybe evidence of? If at every point, the wage of individuals with the same IQ, so we think about what's the interpretation of beta 2. It's the predicted change in wage if all other variables are held constant. So the thought experiment is two individuals with the same IQ. What's their predicted wage? One of them's black, one of them's not. Here, if beta 2 is negative, that's telling me that at every IQ level, even though IQ is constant, the same, black individuals will be paid less. That would be evidence of discrimination, right? So using these dummy variables and being able to hold constant these other factors, we can start to make statements about whether or not it looks like maybe there's discrimination going on in wage data, right? And this could be any group, right? I just kind of chose this because that's the variables I had in the data set. We could also think about, let me see, I don't think I have this in the slides. So I'll kind of draw you another one, kind of think about this, just because I think it's helpful to go through these thought experiments. So if we went back to our example where, let's think about this, slightly different example, but let's say I had this dummy variable of student athlete. And this is where it doesn't matter, beta 1, beta 2, I can write these in different orders. So we want to make sure we can still make the interpretations. And maybe this was, what do I want here? Let's not do this. Let's do predicted GPA based off their incoming SAT scores. Okay. So if I'm thinking about kind of the scatter plot here, and I want to know the relationship between the SAT score and my predicted GPA. If I had student athletes, so this would be when athlete is equal to 1. What is their predicted wage if their SAT score was 0? So I can go back to my regression. If the SAT score was 0, what's the predicted value of GPA if I have a student athlete? It would be beta 0 plus beta 1. Now, what's the interpretation of beta 2? Holding constant the other variable, student athlete, what is the predicted increase in my GPA as that student's SAT score increases, right? So now the slope, because my continuous variable I'm looking at as SAT, would be beta 2. Now, if I'm thinking about when I estimate a regression like this, we aren't going to talk about this until after the midterm, but we can identify maybe the effect of SAT is different for athletes versus not. We're not going to dive into that yet. That's a whole nother topic called nonlinearities, right? For right now, when we include this dummy variable, it's just allowing us to find different starting points. So that beta 2, when I make this prediction for a non-student athlete, what is the predicted value of the GPA score when I have a non-student athlete? We would start out with an SAT of 0. They're a non-student athlete. So maybe here this would simply be the intercept, right? And then what's the line of best fit for that group? Well, it's still beta 2. We still have that same relationship between SAT scores and GPA, but it's just essentially shifting that line of best fit for whatever group is coded as a 1, okay? Now, I don't know where these lines of best fit, right? Maybe beta 1's negative or positive. The way I've drawn it here, what must be true about the sign of beta 1? That being a student athlete actually increases your GPA. Imagination would be it's the opposite likely, right? You have more time commitments and it's probably going to be more difficult given the same SAT score to perform as well in college. But who knows until we look at the data, right? Maybe because they have to time manage, they have better time management skills than some incoming freshmen. I sometimes see that in B251. My student athletes are a little bit more on top of things than the ones that are. Okay. Any questions over anything here? Okay, so we're now kind of moving towards more statements that are more closer to causation as opposed to just correlation. Okay, so we can kind of think about, I think I mentioned this last class, but really when it comes to statistical significance, nothing changes with multiple linear regression. We still assume that the slope coefficient is equal to 0. If it's equal to 0, we always have a two-tailed test, right? We still use the p-values we can use, and I saw a lot of people get this right in the second problem set, which I forgot to mention is now graded, so you should be able to kind of see that up on Canvas. But we can look at our p-value, compare that to alpha. We can look at our critical value, compare that to the test statistic, or we can see if what value is in our confidence interval. 0, right? If 0 is in our confidence interval, can we reject the null? No. Confidence interval tells us the possible true values. So if one of those values is 0, and we always assume that that coefficient is equal to 0, we can't reject it. Could be one of the possible true values. Okay? So nothing really changes with statistical significance. And I showed you this slide earlier with simple linear regression, but we didn't have to address any of these issues. When we start to include dummy variables and we start to look at multiple linear regression, we start to have to focus a little bit more on this kind of condition that we assume is true, which is this fourth one. So the first thing that we had is like the expected value of our error for every value of x is equal to 0. This was kind of related to like our hetero-homoscedasticity. We're now going to focus more on this fourth assumption. So this fourth assumption says that no variable can be an exact linear function of another that you include in the regression. So I'll show you a very obvious one that would kind of violate this, right? So if all these are met, we say that our coefficient is blue. This is just kind of some terminology. We won't really even use that much in this class. But if I start to include multiple linear regressions, kind of what can go wrong, okay? So perfect multicollinearity, what would go against that fourth assumption is that there's no two variables that are direct linear functions of each other. So what if I do something like this? If I try to include the same variable twice, what is for sure going to, every time, let's say I had whether or not a ticket was issued at a traffic stop, so this is one of the data sets we'll look at, and I had whether or not the driver was coded as male. If I try to include the same variable twice on the right-hand side, what is definitely true? Every time driver being equal to male, or sorry, driver being male is equal to 1, driver being male is also going to be equal to 1. Right? So they're always going to be the same value. Are they direct linear relationships of each other? Yeah, they're always the same value, right? I mean, if I know that driver being equal to male is 1, I also know driver being equal to male is, or driver being male is equal to 1. That's the same variable. So Stata kind of saves us from making this error, where if it identifies perfect multicollinearity, it'll often just drop that variable for us, right? But in a problem that I could ask in the quiz or the midterm, maybe I give you something slightly that's maybe a little bit harder, right? So if I try to include the same variable, Stata helps us and it identifies that, and drop says you can't do that. You can only include the variable one time, right? Now, what if I instead try to include an indicator for whether or not, here I won't use the male-female example, but let's say I had an indicator for whether or not the age was above 60. And then I had, that's 1 if the driver was over 60. But I also had a variable which was if the driver is 60 or under, then it's equal to 1. Now, if I include those, are they going to be multicollinear? Well, every time the driver is over 60, and that variable is equal to 1, what does the variable of being 60 or less have to be? 0. Right? I can't be 62 and 59 at the same time. Right? So if I have an indicator variable that says, are you over 60? When that's 1, the variable that says, am I 60 or younger, that would always be 0. They're direct linear relationships. So I have to think kind of hard about these dummy variables. I want to make sure that I don't have any of that going on. Okay. Now, Stata can identify this perfect multicollinearity, which is really helpful. We don't have to spend as much time on it. So I'll kind of gloss over this for a second. We kind of already went through that scatter plot example, so that's why I have this slide open. But I want to think a little bit harder about what if we start to include multiple dummy variables, right? So I don't just have to use one, right? I don't have to make race a binary variable. In fact, we know that there are several races, right? And so what if I want to include multiple dummy variables? So let's say I had an example here where I'm trying to go back and predict wages, and I have dummy variables for what the highest level of education someone has. Okay? So if the highest level of education they have is a high school degree, I put a 1 there for that variable. If it's some college, but not a college degree, it's 1. If it's a college degree, is their highest one. And then if it's a graduate degree, is one. So I have to belong, right, to one of these categories, except what? What group did I actually leave out here? It's not going to be very common, but I could have less than a high school degree, right? So what's going to be true when we have these multiple groups is I can include all these dummy variables. But if all of these are equal to 0, what would the variable of less than a high school degree have to be equal to? 1. Anytime one of these is equal to 1, what does the value of less than a high school degree have to be? 0. There would be direct linear relationships. So if I have multiple dummy variables that are really trying to capture one thing, so this would be an example where in the data, I don't have continuous education. I think some of the stuff we've used, we do have the number of years. Let's say the data comes in and it only identifies kind of the degree level they have, right? So I have these multiple dummy variables. I have to leave one of them out. Because what would the interpretation of my graduate degree be? If an individual belongs to that group, right, the dummy variable goes from 0 to 1. So if I have a graduate degree relative to not, holding everything else in the regression constant, what's the change in my predicted wages? Well, if I hold everything else in this regression constant, all of these would be 0, and this variable is equal to 1. So what am I comparing to? I'm comparing to the group that was left out. So I have to leave one group out, right? If I don't, I have perfect multilinearity, right? Because as soon as I know one of these variables, I would know all the others, right? So we maybe can think about which one makes the most sense to leave out. Well, I left it out here naturally. If I ran this regression and left out less than a high school degree, what would you expect to be true about the coefficients on each one of these dummy variables? So remember, it would be the predicted value of going from 0 to 1. So we could think about high school degree. It would be the predicted increase or decrease in wages from having a high school degree relative to the group I left out. Not a college degree, the group I left out. So what is the group I left out here? Having less than a high school degree. So what would you expect the sign of the coefficient on a high school degree to be? Compared to those with less than a high school degree, I would expect it is probably positive. Well, then what would be true about having some college? Remember, it's not relative to now high school, it's relative to the group I left out. So it's relative to having less than a high school degree. So it's likely the coefficient on some colleges is still going to be positive, but the predicted change in wages, do you think it's going to be higher or lower than just having a high school degree? Probably higher. So when we're leaving out a group, what makes the most sense? Probably to leave out the group that's going to have the lowest value, which is why I chose high school degree here. If you want to think about if we didn't have any other continuous variables and we're only including these kind of dummy variables, really what we're getting at, if I'm thinking about making, I had wages here, predictions for wage. If I had, so I'll kind of write this out. So I'll kind of abbreviate. So this was having high school degree as my highest degree, some college, graduate degree. I'm abbreviating these variables. So what would the interpretation of beta 0 be? If all other variables are equal to 0, so I don't have a high school degree, I don't have some college, I don't have a college degree, I don't have a graduate degree, this is my predicted wage. Or essentially, this is my predicted wage for somebody who has less than whoever I left out, less than a high school degree. Now, what would the predicted wages be for someone that had the highest degree of being high school? Well, it's going to be the predicted change in wage from having a high school degree if all other variables are equal to 0, right? So I would expect it's likely that for my high school prediction, I'm going to have beta 0 plus beta 1. I expect it to be higher, which is why I'm drawing it this way. And then what would I expect about the predictions for someone with some college? It's that constant, but now plus the coefficient on having some college. So I would think beta 2 is larger probably than beta 1. And that, I think makes sense in this context, because as I have more and more education, why am I getting more education? I'm expecting that my wages are going to be higher, right? So we typically would want to leave out the group that has the lowest amount, because then we kind of have this nice ordinal comparison. Now, it's not always easy to do that, right? It's not easy. In this example, it was. I'm sorry, this looks like a 0. This is supposed to be a G. What else could I leave out here? What group could I leave out instead that would make my predictions make kind of nice interpretable sense? So what if instead of leaving out less than a high school degree, I left out the highest category, graduate degree? What would happen to all of my coefficients? The signs would likely now be negative. Because now the comparison is to the group I left out, which is having a graduate degree, which is who we expect to have the highest possible wages, or highest predicted wages, I should say. So when I change the group I leave out, it'll change the sign of my coefficients, but it wouldn't change kind of the size. It'll still tell me the same directional changes, okay? So I think I have a different example in here. So this example, I think it makes most sense to leave out the highest or lowest. Sometimes we're not going to know unless we look at the data. So we just have to use our best judgment. So I had one here where I had some data laying around that was, what is the athletic revenue of a school? And then what conference do they belong to? So we belong to the Big Ten, IU. I taught at Ball State before this. They were in the MAC. So I have all these identifiers for what conference the university belonged to. So what do I have to make sure I do here? If I have every single conference, I still need to make sure that I'm doing what? Well, I have to belong, let's assume I belong to some conference. Right? If I include all the conferences, I'm going to have perfect multilinearity. As soon as I know that IU belongs to the Big Ten, I know, so that's a 1. Every other variable, every other conference would be equal to 0. So I have to make sure I leave one of these groups out. If I knew ahead of time what conference had the lowest predicted revenue, that's probably the one I want to leave out. Some of these small conferences, I don't know ahead of time, right? So what we can do, right, is include an indicator for every conference, and we have to just use our best judgment about which one to leave out, right? We can kind of see here, there are some that are what we call independent, so they don't belong to a conference. So that's going to be the one that I leave out here. Now, if you just allow Stata to pick and choose, it'll just randomly choose one, right? So you'll notice it chose independent here, but like, what's actually going to be the conference that has the lowest predicted total revenue? It's going to be whichever one has what kind of coefficient? Negative, but the largest negative coefficient, all right? Because my predicted total revenue for that conference would be the intercept, or the constant, plus the coefficient associated with that conference. So if we look through here, this is one of those data sets where I would expect you to know this on the quiz or exam. If I have these e to the positive or e to the negative, what does that mean? Take the value and move the decimal. If it's positive, that many places to the right. If it's negative, that many places to the left. These are athletic revenues, so they're large amount. They're large the values, right? So here, what's the largest negative value I have? Yeah, so some people look at this and get confused and say, oh, it's got to be the Mountain West. Well, that doesn't have an E to it, right? If I actually think about like the MAC, that would actually be what? Negative, move this decimal 7 places. That wouldn't be like 3 million, that would be like 18 million, right? So the value that's actually largest here, if I'm looking at these negative values, well, the MAC's pretty high, right? Negative 1.8 to the 7th, move the decimal 7 places. Sunbelt's a little bit higher, right? And I say higher, larger in absolute value. So this is actually going to be the conference that has the lowest predicted revenues. In fact, if I looked at these coefficients, what could I do? I could order these conferences in terms of predicted revenue. Who would have the lowest predicted revenue? A university that belongs to the Sunbelt. Then who would have the next lowest predicted revenue? MAC. Who would have the next lowest? Conference USA, I think is what that one stands for. Then Mountain West. Well, now I start to get the positive values, but I can still order them, right? So then it looks like AAC. Oh, but I made one mistake here. If I'm going from the negative to the positive, what group did I skip? The one I left out. So in this example, when I didn't know which group to leave out, the one that I left out, right, the predicted value is going to be the intercept. if I have a positive value, that tells me that the conference is going to have predicted revenues above that group I left out. So once I get through these negative values, if I'm ranking them after this Mountain West, it would then go independent. And then I start to go to the predicted, what has predicted higher revenue. Now the conferences that have a positive coefficient, right? Because now I'm adding in that positive coefficient to their predicted total revenues. And then from there, it's just going up to higher values. Does that make sense? Any questions on this idea? Now, once again, I think I'm even I said like kind of which one would have the highest. Well, we're just looking for the highest possible value there, which is what? The SEC, right? I think I have here, let's see, now I didn't put it in here. I thought I had a cheeky comment. Where did I go? I went back too far. Oh, it's later on. All right, so we want to go, okay. So we can rank order these. Now, I've included just the dummy variables. I could start to include continuous variables as well. And now the interpretations of these coefficients stay the same, but I have to add on the word of what. So let's say I had the same regression, but I included the university's total enrollment of students, right? Or maybe total alumni. But now the interpretation of these coefficients would be the change in the expected revenue if my university belonged to the Sun Belt, holding everything else constant, or holding the total enrollment of that university constant. So those start to become a lot more powerful statements. So I can include multiple dummy variables, but at the same time, I can include those continuous variables, try to increase my R squared as well, right? Or make better predictions. Okay? So I think like right now, I just saw something the other day. I don't know if it was true. Social media, should probably verify more than what I see, but it's something like the Big Ten is talking about expanding to like 24 teams or something ridiculous. And here, if I'm thinking about if I was an independent, so people talk about this with Notre Dame a lot, they're not in a conference. If they were, which one would they want to join? The SEC, if they're just worrying about total revenue predictions, right? Now, there might come, this is total revenue. If I'm factoring in, I don't want to just look at revenue, I also want to look at costs, and right, not being in the South, I would expect the costs are quite a bit higher as well. So I'd actually want a regression where I not only try to predict total revenues, I want a regression where I try to predict total costs, looking at the difference between the two, kind of relating this to like economic concepts you probably heard in other classes.
This is like incredibly related. And how does that work for like the Big Ten expanding to give schools on the West Coast to be part of it? Like obviously they're not Midwestern schools, so like how does that cost back?
Our predictions would be higher. Our work would be more difficult, right? Because we now want to start to include variables like how many markets are my teams in? Well, I can then hold that constant and see as joining the Big Ten versus the SEC battery. Right? So I just would be adding in more data essentially to make a more correct decision if I'm a conference or a team thinking about joining a conference or not. Okay. This is very simple, right? We've left out a lot of additional controls. Okay. All right. So kind of talk through this. So I want to make sure we get some work with Stata here. Got some traffic stop stuff. So let's go to the MLR week 6 file. So I tried to I updated the one from last week to kind of stop where we left off. This one kind of picks up, right, where we were at. So, and I forgot to include my path when I copy and pasted this. Oops. So you get to see me hunt for where I have this data on my OneDrive. So it looks like I had it here. I think I just put it under week 6. So I'm going to open up that revenue data. If you downloaded this ahead of time, you would have had this as your file path or whatever file path you would have. So just as a reminder, since I didn't include it, we can always set our path by opening that file manually and just selecting all those folders and subfolders. Once again, whoa, what am I doing? No, stop. Okay, one of my buttons must have been stuck on the keyboard. All right, there we go. So here, yours should probably always be the same. I said just create one folder, and we opened up that NCAA revenue data. So we now should be able to see I've got expense data even in here. So this gets at my costs. I've got corporate sponsorship. I've got donor contributions. I have a ton of different variables now in this data set where I can start to run some regressions. So this command, I'm just going to throw this in here. This allows us to have a more accurate data set. So a lot of times what you'll want to do if you're working with data, so this is where it probably isn't something that might not going to pop up on the exam, but I'm trying to give you things that allow you to work with data outside of this class. So when you have a data set and you download it as this raw data, sometimes you're going to have some weird things, right? So in some of this, it didn't have an identifier for what conference the team belonged to. It wasn't just whether or not it was independent, it was just missing. I think this was like D3 schools were in this data set, and so it just had some missing values. So sometimes you'll want to do what we call clean the data, right? I have some observations that are just missing values, right? So I want to get rid of those, right? Because when I start to run these regressions, if I'm missing values for these data sets, if I try to include variables that use those, I can't use that data. There's nothing there. So this keep command will only keep the observations if, and this is where we were looking at statements before, if I want not equal to, so equal, we had to put two equal signs. The reason why is because if I want not equal to, I had to use that kind of exclamation point. So what this is saying is keep the data only if it's not missing this conference variable. Okay, so I'm going to run that real quick. And then if we want to look at instead of just like eyeballing the data, if we ever want to see all the possible values of a variable, we can use that tab command. So I'm going to kind of hit tab. Here's all the different conferences that exist. So these are the ones that we were looking at before, okay? And it even tells me the number of observations I have in each conference, okay? So what I could do is go through, let's not do this for a second. I could go through every single possible response and say, create a dummy variable that is AAC if the conference is equal to American Athletic Conference. Create the Big Ten dummy variable if the conference variable is equal to Big Ten Conference. But that's a lot of code to have to go through every single conference. Now here, I would only need what, like 10 lines of code? Imagine if I was going to do this for something like every university, I wanted to create a dummy variable for that university. Like let's say a different example, like maybe I want to try to predict the wage, the first wage of a student given their GPA, but I know that's going to vary depending on what school they went to. I then want to include a dummy variable for every single school. Can I manually go through and do this? I mean, I could do this by hand, but it'd take me forever, right? So we can create these variables manually, but we can also kind of do this nice little loop, right? Now, I wouldn't expect you to know how to do this. I'm not going to have you do this for a data set or a problem set. In fact, I'll show you an easier way. You can actually loop through this and create different variables for every single conference, right? So if you give it a list, you can tell Stata, go through this variable. First AAC, create the AAC variable if conference is equal to AAC. Then go to the next one. Create a variable called Big Ten if the conference is equal to Big Ten. It then loops through all these possible values and creates all these dummy variables, and all you had to do was type in one line of code instead. So I can do that. So if I looked at my data before, I have the conference name, but I don't have any dummy variables for that, right? So if I run this line of code, it'll go through that conference variable and now create all these dummy variables for me, okay? Now, I can do that, right? And I can start to run regressions. We're going to kind of skip through this, right? We talked through like leaving out the lowest group, leaving out the highest. There is a much easier command that we can use in Stata, okay? So if instead of creating these dummy variables, this is where in like my example, if I wanted to include a dummy for every college, it's going to be, I'm going to have a million right-hand side variables there. What I can do, let's say I wanted to try to predict this total revenue. I have this conference abbreviation variable, right? If I use this IDOT command, that should create a dummy variable for every unique value for that variable. So it should go through that variable of conference and say, okay, if conference ABB is equal to 1, create a dummy variable for that. If it's equal to 2, create a dummy variable for that, so on and so forth. The problem is, if I try to run this command and I go to Stata, it's going to give me an error because we haven't really had to deal with this too much yet. If I see red in the data set, Stata is not treating this as a number. It's treating it as text. It can't use that IDOT command with text. It can only use it with numbers. But there's a really easy, Jesus Christ, is the building going to collapse on us? Sorry. So there's an easy way to fix this. Because if I know that the Big 10, right, is one of the values that I could see for that, or one of the text I could see, well, maybe I just assign the Big 10 the value of 3. And I assign the SEC a value of 7. And I assign this other conference a value of 1. I can basically replace unique text with unique numbers, right? Now, I don't want to do that manually. So we have this nice kind of code in Stata which says, take this variable that I know is text. I can't do anything. I can't run a regression using text. I have to use actual numbers. So I want to encode this variable and create or generate this new variable. So what I typically do if I'm doing this just to keep track of things, if I have a text variable, to make it into a numerical value, I'll call it, like, instead of conference abbreviation, conference reg. That reminds me, this is the variable I can actually use in my regression. Okay? So if I encode this variable, notice every time that conference text is equal to Sunbelt, it looks like it's Sunbelt, but what happened to the color? It would turn blue. If I actually click on this, the Sunbelt is a value of 10, right? Every time there's Sunbelt, the value is 10. Every time it's Mac, so if I go over to the original text variable, this was showing up as text. But when I encoded it, the new variable I created, which was conference reg, now the Mac is always assigned the value of 6. So it's converted all of my text into numbers. So once I have these numbers, then I can actually go run this regression where I'm trying to predict total revenue. And now when I use this IDOT command, what it will do is essentially go through this process and create a dummy variable behind the scenes where I have a 1, 0 for every single possible conference. And then it chooses which one it leaves out, right? So if I go down here and I run this regression, I get all those coefficients. Now, it doesn't tell me which one it left out, which is kind of problematic, right? Because then I ultimately need to, like, figure out which one did it leave out here. Well, what could I do? I could tab that conference abbreviation variable, and looks like what? So I've got, oh, AAC isn't included. That must be the one it left out, right? Every other kind of possible value, I've got the Big 10, I've got the Big 12, et cetera, right? So it's always going to leave one out. I think what it defaults to, and this would support me, but I'm not sure, 100% sure this is true. I think it goes based off of alphabetical order, which one it leaves out. But there's probably ways in which you can change that with some different settings. So here, if I encode these variables, I can then very quickly include multiple dummy variables from a text variable, right? So I can take what downloaded as non-numerical data, and I can kind of create numerical variables that I can then include in my regression. Any questions on that idea? It's just a helpful thing. You might have to do this on the problem set, or I might give you like a text variable and you have to kind of use that encode command so that you can then use the IDOT command in your regression. Now, if I wanted to, if I look at this data, now that I have these dummy variables, so the kind of nice thing is when I ran the IDOT command, it doesn't actually create these variables. Remember, I created these by hand. So it doesn't actually create them in my data set. It does all of it behind the scenes and just kind of stores it temporarily. This might seem like a very non-issue, but I have a data set right now that I'm working with where I have free throw data from I forget how many years, and I've got like 3,500,000 observations. If I create the variables in my data set gets way too large, right? Because it's taking up like more memory. So when you have really large data sets, this IDOT command doesn't save it in the data. It just temporarily creates it. So it saves a lot of memory space, right? It's a little bit more outside the scope of this class, but just as you're kind of thinking about using these tools, once you get out there in the real world, that's why we like to do this IDOT command as opposed to creating all those variables ourselves in the actual data set. But if we look at these, I could start to include like ticket sales. Ticket sales should be kind of related to revenue. So what might I do? Like donor contributions. So even when I include these multiple dummy variables, I can include other variables as well. So if I run the same regression, it'll still include all those dummy variables, but it can also include continuous variables. And now this is like the predicted change in my total revenue if I belong to the Sun Belt, holding constant what my current donor contributions are. And I can include even more variables, right? So if I look down here, what's another one? I could look at student fees, right? So maybe I want to include also as an additional control, student fees. If I can spell, right? So now these interpretations start to move further away from correlations and closer to causal, because now this is the expected change in my total revenues, holding constant these other things. So now the thought experiment is, if I had two universities, the same number of kind of contributions from donors, the same amount of student fees, but one of them belongs to this other conference, what's the predicted change in their total revenues? I'm getting closer and closer to causal relationships. Okay. Any questions there before we keep moving? Okay. So I'm going to open up a new data set, which is this traffic data set, and touch on some of the things that we talked about already. So I've got that traffic stop data. It opens it up. I then kind of have, this is where sometimes I might have a variable. And I think here, let's see if I can find it real quick. Oh, I don't want to make this point. So this has got the reason for the stop, and this also has the result of the stop. So this is where you probably wouldn't have known this ahead of time. I actually had to go back to the code book for this data, and the result of the stop told me when this traffic stop occurred, did it result in a ticket being issued, no ticket, arrest? I forget all the different possible, but they're all coded as numbers. So sometimes we have the issue of the data comes in coded as text and we have to convert it into numbers. Sometimes it comes in coded as numbers and we have to remember what those actually represent. So here I believe the result of the stop, if it was equal to 2, that meant that a ticket was issued. So I'm going to create this new dummy variable, which is whether or not a ticket was issued. And it's equal to 1 if the result of that stop variable is equal to 2. That's just how it was coded in the data set. Okay. So I'm going to create this variable. Now here's where I showed you this output earlier. If I try to include the same variable twice, state is like, you dummy, you can't do that. Right? It's going to be perfectly multicollinear. Right? So that kind of saves us there. Now let's say I tried to create a variable for every single possible race. Right? So here, once again, the driver's race didn't come in as text, it came as a number. So every time there was a 1, that was coded by the police officer who made the stop, that was an individual who they, from their driver's record or whatever, identified as an Asian individual. And then, 1, it was equal to 4, that was Hispanic, so on and so forth, right? Now, obviously, like, race is a much more nuanced conversation, but in terms of like the traffic stop data, it was coded like this, okay? So I'm going to create all these indicator variables. And because I have this other category, I've essentially covered every possibility, right? So I'm going to create these variables. And then I'm going to try to predict whether or not a ticket was issued using all of these dummy variables. Now, what should be true if I try to include all of them? If I know that someone's race is Hispanic, what is every other race dummy variable going to be equal to? So they are direct linear relationships. I have perfect multicollinearity. I have to leave one of these groups out. Now, the nice thing is, if I run this, status saves us. I think in the slides, like I said, I had some cheeky comment about status saves us again, right? It can identify perfect multicollinearity. On Thursday, we'll talk about imperfect multicollinearity, but in terms of perfect, it can identify that and it'll drop one of those variables for you to make sure you avoid that mistake, okay? So here, it's kind of interesting, right? I guess, who has kind of the highest predicted probability if they're being stopped of being issued a ticket? Individuals who are Asian. The lowest likelihood would be if you're identified as Hispanic. Now, we've omitted a lot of other really important information here. Like, well, what was the reason for the stop? Was it because you were speeding or was it because you had a warrant out for your arrest? Right? So like, we're ignoring a lot of other important things and we're ignoring age or things like that. So, when we start to kind of look at more complicated regressions, we're going to want to include things like, well, what was the reason for the stop? Right? So here I just did a thing where I said, okay, I want to include all these kind of identifiers for whether or not the officer was of these different races as well. Because maybe there's like discrimination coming from white officers to every individual who's non-white, but maybe officers who are considered, Hispanic or more likely to be, right? So I want to control for that. There might be some kind of cross-race preferential or discriminatory treatment by the officers, right? So I'm going to create these variables and then include them in my regression as well. Now, compared to when I only included the driver's race, what should happen to my R squared when I include the officer's race? I'm including more variables, so my R squared should go up. Now you'll notice here, what's the difference between my R squared and adjusted R squared? It's really, really small. Why? So the variables are going to create that difference between the R squared and adjusted R squared. Now I have a relatively low number of variables, but what's going to drive that adjusted R squared and R squared gap to be really small even more? My observations. How many observations do I have here? Almost 80,000, right? So that difference is going to be really, really small. Now, if I then kind of look at this like officers, so I add these in. I think I created these. Did I? Yeah, I created them already. So I'm now going to include those, but I also have the reason for the stop. So now the interpretation of these variables is going to be holding constant the reason for the stop. So these are going to be a lot more closer to causal relationship interpretations. So if I do something like that, now I don't know what these reasons represent, but I know that I'm holding constant what that reason is. So it doesn't matter that I don't know what those reasons are. The interpretations say now of, and here I had like officers, I included a bunch of variables here I forgot about. Officers' years of service, whether or not the officer was male. So now notice if I look at this kind of indicator on whether or not the driver was black before, without these additional controls, it was positive, not quite statistically significant, right? P-value of 0.3. So here I'm like, oh, okay. Drivers who are black aren't issued tickets at any higher rates, right? I can't reject the null. Well, I haven't controlled for a lot of other factors. In fact, if I control for a lot of other factors, now notice what happens to that coefficient on whether or not individual, the driver who's identified as black, the probability they're issued a ticket. Remember, when we have a dummy variable as our Y variable, changes are the changes in the predicted probability that variable is equal to 1. Well, now I actually get a negative coefficient. So black drivers are actually less likely to be issued a ticket, and it's statistically significant at the 90 and 95% level. Now, the reason why that can change is because now the interpretation of the variable is still the predicted change in the probability that an individual is issued a ticket if they're black, but holding constant the officer's race, officer's years of service, officer's gender, and the reason for the stop. It's a lot more powerful statement, right? We're not just relying on correlations. We're getting much and much closer to a causal relationship. But a regression like this still allows us to identify if discrimination is occurring. The fact that some of these coefficients are statistically significant, some are positive, some are negative, tells us that holding all these other factors constant, officers' years of service, the reason for the stop, the officer's race, that they're still issuing tickets at different rates to these different races. That's telling me that like something's going on in terms of different races are being treated differently, right? And so this is, I think, I like this example because it might seem dumb. It's like whether or not you get a traffic stop. But what if instead I change this? In fact, I might have forgot to create it here. Hopefully I didn't. Let's see. Yeah, so one of these, when I created this variable up here, which was equal to ticket if the result of the stop was 2, one of the other numbers there meant the traffic stop resulted in an arrest, right? So that's a lot more. So maybe I don't have strong identification of maybe like large discrimination if someone's issued a ticket or not. But if I run this regression, all the same controls, but now my dependent variable is whether or not they were arrested, right? Now notice when I'm looking at kind of these racial things, there's some statistically significant results. And it's saying that holding all these other factors constant. So this is the thought experiment. 2 officers with the same years of service, same gender, same race, right? Same reason for the stop. So this is controlling for like, did the stop occur because the individual was speeding? We're holding all that constant. Now the probability that someone's arrested at a traffic stop, if they're black, goes up by 0.01, right? I mean, holding all that else constant, I don't have a lot of other explanation for other than there's some discrimination going on, right? So maybe there wasn't large discrimination going on whether a ticket was issued, but like we probably care a lot less about it discrimination. I mean, we still care, right? But being issued a ticket is a lot less significant in someone's life than being arrested at a traffic stop. And once again, this is holding like the reason for the traffic stop constant. This is crazy, right? This is a crazy result. And if I was a politician, I'd be like, yeah, we need to fix something here, right? I mean, you know, we could add in more variables and maybe we kind of control for some other omitted variable bias that we talked about last week, but this is a troubling result, right? So also kind of notice as I added in more variables, my R squared, I kind of led this earlier, went up quite a bit, right? It went from like, if I just used the driver's race, it was 0.0014. If I included all these other controls, it's up to about 0.11 or 11%. So as we add in more of these control variables, right, we're going to get a higher R squared. Now the gap in between the R squared and adjusted R squared doesn't look like it changed much here. And the reason why is because even if I add in more variables, if my sample size is really high, it doesn't matter as much, right? That scaling proportion of n minus 1 over n minus k minus 1, if n is 80,000, increasing k from 10 to 20 isn't going to have near as much of an impact on that difference between my adjusted and my actual R squared. So we will kind of stop there. I'll revisit on Thursday's class some like perfect multicollinearity. We're then going to start to talk about imperfect multicollinearity, just working through more of these examples. I think we'll probably revisit what we talked about last Thursday, which was doing some more of this calculation of, even in my last regression, I don't know, maybe I do have omitted variable bias of like the number of years that the drivers had a driver's license. I don't know, there was like weird things I left out. So we still want to be able to think about, okay, why might those coefficients, yes, it looks like we have evidence of discrimination, but what's maybe still some omitted variable bias that might exist? And can we calculate what that bias would be? We can calculate the value usually, but more so we usually care about just the directional change, right? So we'll kind of revisit and talk through more of this similar example, pretty similar content, other than we'll be going through imperfect multicollinearity, right? Everything you should need for that problem set in the quiz that get posted tomorrow, we've already covered, okay? Other than that, any questions for me before we keep moving? Actually, sorry, I said that. There might be one question still in the problem set we'll cover on Tuesday's class, but you can get through the vast majority. Or did I say Tuesday? Sorry, the beginning of Thursday's class. Yeah. Okay. All right. I will see you guys on Thursday.